Before we begin today's session, I'd like to run through a few housekeeping logistics. Today's seminar is vaccine safety evaluation using the self-controlled case series method. In just a moment, we will introduce our speaker. You may notice right now that all lines are muted to help reduce background noise, and the recording has just started. A copy of this will be available after on Vimeo, and our speaker has graciously agreed to share her slides for those who are interested. So we will make that available as well. While you are in the presentation, you will have the opportunity to ask questions both in the chat as well in the Q&A function. I will be monitoring the Q&A throughout, and we will have time at the end of today's presentation to address them. So stay tuned, and we look forward to addressing your questions as we go. But most importantly, I'd love to turn it over to Dr. Louisa Smith to introduce today's speaker. Louisa?
Thanks, Kristen. I have the pleasure of introducing Dr. Heather Whitaker today. Her past research has primarily focused on self-controlled designs in epidemiology, and she's recognized as a leading expert on the self-controlled case series method. As you'll hear about today, this design is used to study temporal triggers and is frequently used in vaccine safety research. Dr. Whitaker has been committed to both innovative development of methods, as well as advocating the appropriate use of methodology. She maintains a dedicated website and has advised numerous epidemiologists from all over the globe on study design, computation, and interpretation. Dr. Whitaker is now working at UK Health Security Agency, which is formerly Public Health England, where her work has focused on studies of vaccine effectiveness and antibody studies and surveys. So I'll give Dr. Whitaker the floor. Thanks.
Thank you very much for the warm welcome. All right, let's share my screen. Hopefully you can all see that now.
Perfect.
Great. Okay, so I've just got my disclosure slide for starting. There was some grant funding associated with work, and that's acknowledged here, but otherwise I have nothing to disclose. So a brief outline of the talk. So I'll just start off with a single slide on where self-control case series fits into the vaccine safety evaluation. I'll start from the beginning and give a full introduction to self-control case series for those of you who are not familiar with it, although I am well aware that there's going to be plenty of people here who are using it or are kind of experts in their own right. I'll run through the main advantages, the limitations and the assumptions, and some of the things that we can do when those assumptions are not met. There's not been a huge number of studies published so far on COVID-19 vaccine safety evaluation that have used self-control case series. There's a couple of papers and we'll just have a look at those. And then if there's time, I'll just mention a little bit more about the self-control risk interval design. So starting with vaccine safety processes. So I'm sure many of you are quite familiar with this work. So there's the reactive monitoring. So these are just the spontaneous reports of adverse events that come in to obtain signals. In the UK, we have the yellow card scheme. I'm not sure what your equivalent is over in the US, but this is not something self-control case series comes into. And then there's more proactive surveillance. So this is using large databases to look at specific adverse events and vaccines to detect signals. They can actually show associations if they're well designed. And typically a simplified self-control case series design, which has now been coined the self-control risk interval design, can be used for suitable adverse events. And then more where self-control case series has been used is in the sort of end epidemiological studies but are done to test whether signals found are evidence of a genuine adverse vaccine reaction. It's now pretty well established and it's got over 20 years history of use. So we'll start with the basic introduction of what is the self-control case series method. So we're looking at temporal associations, when rather than who within cases. We're aiming to estimate a relative incidence or an incidence rate ratio, and that's just the factor by which the outcome rate is increased during pre-specified exposure or post-vaccination risk windows. So I've got a little diagram at the bottom. So say a vaccination occurs here. I'm not sure if you can see my cursor actually, probably not, but the blue here is showing those post-vaccination risk windows relative to windows before and after exposure-related risk, which are in the grey. The outcomes that we can study, they can either be recurrent and independent, or they can be non-recurrent and rare. So certainly we can have multiple outcomes as long as the timing of those are independent. What's unusual about self-control case series in comparison to other designs is that the follow-up is not censored at the outcomes, and the exposure history over an entire time a case is observed is used. So it's a conditional cohort method. The exposures are regarded as fixed and the event times are random. And unlike a cohort method, the follow-up is not censored at the event time. Only cases are required, no controls. Estimation is self-matched within individuals and all fixed confounders factor out. So how does it work? So we fix an observation period over which outcomes are ascertained. The individuals with outcomes are the cases. So these observation periods, they might be just simply, if we're looking at COVID-19 vaccine safety surveillance, we would probably be looking from the beginning of the vaccination program, perhaps just up until the time that a database extract has been taken, and that might be an observation period. But they can be set up with respect to the times of the vaccines themselves, or ages, or any calendar time period, just as long as those observation periods are not in relation to the times of the events themselves. So we obtain the exposure histories over that period, and then we subdivide our observation periods into exposure risk windows and age group windows. So yes, we just set up any age group boundaries that we want, or alternatively, they might be calendar time periods. Just what, if we expect to have changing baseline incidents with respect to age or with respect to time, then we'd want to include those factors. The exposure risk windows, it doesn't just have to be a single window, they can be multiple windows. We can add extra washout windows, we can break them up as we wish. We can have separate factors for dose 1 and dose 2. So it's very flexible. As in a cohort study, the exposure history is treated at fixed. And then the number of outcomes experienced is also fixed, and it's just the outcome times which are regarded as random. So it's all about the timing of the events. Unlike other designs, post-outcome exposures are taken into account, and the model is a product multinomial which can be fitted using a conditional Poisson regression. So this is just a kind of data table of the way the data needs to be split up. It just needs to be cut up into little time periods. So our first interval is just in the first age group. This second interval, we've got the first exposure come in, but they're still in the first age group, and so on and so forth. And then we count the numbers of outcomes within periods. So this is happening here in the 7th interval, where we've just got one outcome. And we estimate our exposure effects. We estimate our age effects. There's an overall relative incidence profile. So this self-control case series model, we can show that individual effects cancel out of this model completely, hence the self-control. The non-cases make no contribution, and it models when the events arose in relation to the exposures over the entire observation period, given that an event occurred. So the main advantages: only cases are required, hence data are relatively easy and cheap to assemble. All fixed confounders are controlled. We can model temporal variation in the event rates with respect to age, with respect to time, or whatever's needed. Independent recurrences of the adverse events can be handled in the same framework. And exposure risk periods, they can be long or of indefinite length, when usually we need unexposed cases to be able to do that. I think the important thing is that we have person time in each of the particular exposure categories and age categories. And power is often good, but it's usually best when those exposure risk periods are short. So if it's a transient risk that we're trying to estimate. So here's just some examples looking at some of those advantages. So I mentioned an advantage is using only the cases. We've got an example here, which is looking at convulsions after the measles vaccine. So we estimate the incidence rate ratio of convulsions in the 2nd week after the vaccine. There was a cohort study done, which involved over 600,000 children. They found an incidence rate ratio of 2.83. And the self-control case series study, which was done in '95, had very similar results. And that was based on only 952 cases. So there's a much smaller data set required, and we don't need to worry about controls. So controlling for compounding is another advantage, and we have an example, which is asthma exacerbations and the flu vaccine. So severe asthma sufferers tend to receive flu vaccination. This group did both a retrospective cohort study, where they adjusted for asthma severity by the number of inhalers dispensed, the number of hospitalizations and emergency department visits. And they also did a self-control case series, which automatically controls the asthma severity. These are the results. So the unadjusted cohort gave a biased estimate of 3.29, but after adjustment, that came right down to 1.39, and it was just marginally significant. However, the self-control case series study found no association whatsoever. The relative incidence was very close to 1. And it's thought that perhaps those cohort results were subject to indication bias. So they never quite managed to fully adjust for the asthma severity. Whereas the self-control case series, which would automatically adjust for severity within an individual, as long as that's fixed in time, then it would be unaffected by that bias. Another advantage was that the exposures can be long or indefinite. And as an example of that, we have autism and the MMR vaccine. So there was a study done way back in 2001, which had 257 cases of autism in children aged less than 16 years old, 293 of which had received the MMR vaccine. this study does include unexposed cases. The risk period was indefinite, and we used a semi-parametric version of the self-control case series, which I don't talk about any further in this presentation, but that's a method that does allow quite fine control of the age effects. And you can see that no association was found in that study. This next slide is just kind of for fun. So MMR and autism was one of the earliest uses of self-control case series. And at the time, a method came under a lot of criticism. And here are some of those criticisms. This uncontrolled method is unacceptable in science, was one comment it received. Dr. Andrew Wakefield, who was the person who wrote the original paper on MMR and autism, said, "Such were the anxieties about this study, but it was the subject of a highly critical debate at the Royal Statistical Society. The conclusion was that the study design was wrong. A cynical attempt to disguise the truth, a scandalous dupe of BSE proportions. We demand the resignation of the study authors." However, a comment from one of the referees, but this paper seems to contain rather few commas. Anyway, we're many years on from there now. It's very much an accepted design, and other studies of MMR and autism have confirmed those results that were found that there's no association between the MMR vaccine and autism. And that's been done with cohort and case control methods as well. Limitations and disadvantages. So precise information on the timings are required. So we need precise information on the timings of the vaccines as well as the events. The length and timing of those post-vaccination risk periods may need careful thought. I mean, certainly with the COVID-19 vaccines, we're still learning very much and, trying to understand what the precise windows that we should be looking at are. Temporal confounders can bias results if they're not taken into account. Only estimates of relative incidence within individuals are available, so absolute risks are not estimated. And just make a little comment here. I'm not sure if that has any implications for use of self-control case series results in vaccine benefit risk. It might make it a little bit harder to evaluate. So the self-control case series has some strong assumptions. The events must not influence the occurrence or timing of subsequent exposures, i.e. those exposures must be exogenous. Events must not influence the duration of the observation period. And recurrent timing should be independent. There are some simple workarounds and sensitivity analysis that can be done. Otherwise, there are developments that extend the applicability of the method to situations where these conditions are not met, but at the cost of greater methodological complexity. So let's look at dealing with some of those limitations as assumptions. For time varying confounders. So we're unable to control for unmeasured time varying confounders. I mean, it's certainly true that cohort and case control methods can't either, but probably our self-control case series estimates are more susceptible to biases by time varying confounders. An example would be flu causes Guillain-Barré syndrome, and we're looking at influenza vaccine. This can't generally be fixed, although we could try and quantify the possible bias. We can include age and season effects, which might deal with some of that bias. Independent recurrent events. So the model assumes that events arise in a Poisson process, and that's independent within individuals. So we've seen, for one example, that autism is not recurrent. but that's not so much of a problem as long as the event is rare. Example 2, events tend to occur in clusters. So asthma attacks might be an example. So there's an easy fix there. We can just use the first events as long as the outcomes are relatively rare, or we can put some minimum interval between the events. Or if we want to get a little bit more complicated, we can model the dependence. Note, with these fixes, you would still use a whole observation period. We don't censor at the event. So, excuse me, I seem to be losing my voice. So dealing with limitations and assumptions, the duration of the observation period. So events should not increase the mortality or shorten the observation period. One example where this is violated would be if the outcome is meningitis. Certainly that there is some mortality risk with that. So fix, we can just check if the mortality is fairly low, say less than 10% within the length of a follow-up. And we can just run a sensitivity analysis where we remove those who died. If the outcome is stroke, we can do the same, run a sensitivity analysis, removing those who died. If the results look different, then there is an extension that can be used that allows for survival following the event. I'm not going to go any further into that now, but the paper is cited there. Event-dependent exposures, this is usually our main problem, that events should not influence the occurrence or the timing of subsequent exposures. The assumptions required because the exposure history is regarded as fixed throughout the whole observation period. However, this is often not the case. So with terminal events or death, then post-event exposure is completely and utterly impossible. Contraindications, for example, previous anaphylaxis following a vaccine, reverse causation, if the event causes or inhibits exposure. In fact, I think what we were finding in the UK after there were concerns with the Oxford AstraZeneca vaccine and thromboembolisms, that once patients had had a thromboembolism, that actually put them within one of the COVID-19 vaccine priority groups. So we were seeing patients being vaccinated fairly soon after they'd had a thromboembolism, if it occurred before vaccination. Sampling, the exposure history might just be taken at the event, or delayed exposures until recovery from the event. These are just some examples where that assumption is not met, and I think we can certainly kind of think of lots of situations with vaccinations where that occurs. So failure of this assumption induces bias, and the direction is actually always predictable. But in some cases, we can do a simple adaptation, and we'll have a look at that now. So event-dependent exposures, if we've only got short-term delays. So an example here, a child is in hospital with convulsions, so doesn't get their MMR vaccination when scheduled. So what we see here is a plot which is centered on the day of vaccination. There's a little arrow there pointing to where vaccination occurred. That's day 0. And then we can see that there's a deficit of events just in the 2 weeks prior to vaccination. That shows up in that plot. We can also see at 6 to 11 days after vaccination, there's a big spike. So the fix here is to remove some person time just prior to vaccination from the background. We call this a kind of pre-exposure window. And if it's just a short-term delay, then this trick can correct the bias in the relative incidence. So going back to the MMR vaccine and convulsions example, where we've got that deficit of events in the 2 weeks prior to vaccination, if we take that out of the baseline into its own separate window, we see there's a reduced relative incidence within that window, -14 to 1 days just before vaccination. And this pulls down the relative incidence in that 6 to 11 days risk window just slightly. But what if we've got long-term dependence? Then things get a little bit more complicated. So if we've got long-term delay, or if the vaccination can't occur after an event, then we can get around it by using only post-vaccination time. So in SCCS, the observations can validly be defined in relation to age, time, or exposure, just as long as it's never the adverse event. So post-vaccination risk windows have to be finite in this situation, and preferably short, i.e. the risk returns to baseline. If we're only using post-vaccination time, we can't have an indefinite window, because we'd only have exposed time then. So we redefine our observation periods to start from the time of vaccination up until the study end. And we do this even if the event is or results in death. So since there's only one exposure, or if it's just the final dose and that's been observed, then the subsequent exposure history is known regardless of survival status, and the self-control case series method is still valid. But what if we've got 2 exposures? So consider a 2-dose vaccination schedule. The relative incidence for the second dose risk period can be estimated as the single exposures, and we just look at using time only after dose 2. That's relatively straightforward. But what about those who experience the event before the second dose? So we have a counterfactual method where we aim to proceed as if there have been no second dose. So the relative incidence for the first dose is estimated using study time only after dose 1. However, what we need to do is we need to pull down the relative incidence during the dose 2 risk window down to 1. So it's in line with the baseline and control windows by replacing any event that occurred within that window with an unbiased estimator, which is 1 over the relative incidence for the second risk period. And put that in pictures. It's a complicated method, this one. So if the event occurs after dose 2, as we see for the kind of example at the top, it's all fairly straightforward. We can just use time after dose 2 to estimate the relative incidence after dose 2. And the same for dose 1. When we're doing the estimation for dose 1, we just use that, count that dose 2 window as the baseline. But if an event occurred during that dose 2 window, as we see for the middle example, we need to put some weighting on that period, which has now sort of become part of the baseline period for when we're estimating for dose 1, which is just 1 over the dose 2 relative incidence. And the bottom person here, where they have an event after dose 1, they can make absolutely no contribution to dose 2 because they didn't experience it, and they can just be used to help estimate the relative incidence after dose 1. So individuals who encounter 2 doses are used twice with this method, 1 dose just once, and we use an iterative procedure for estimation of both dose effects. The standard errors need to be estimated. In the R packages, we have sandwich variance estimators, or it can be done by a bootstrapping. Age and period effects can be incorporated without any problem. These are never censored. And unvaccinated individuals can contribute to the estimation of age period effects, but they don't actually make any contribution to exposure effects if they're included. There's an R package, SCCS, which fits this model fairly easily. It can be extended to multiple doses, more than 2. And that situation where we have adverse events with some mortality risk but shorten the observation periods, this is also an alternative solution for those. That method's rather complicated. There might be simpler workarounds in certain situations. So if the doses are known to be separated by some minimal interval that's longer than the vaccination risk window, a much simpler method is available. That's just a standard case series analysis with the observation period equal to the minimal interval between doses. So this is also akin to the self-controlled risk interval design, which but using post-vaccination time only. To put that in pictures, suppose we observe some data. We've got sort of in the turquoise the minimum separation between doses shown at the bottom. So there's 2 doses. For this person, an adverse event occurs after dose 2. So we can just redefine our observation period to be the same length as that minimum separation between doses and just do a very simple analysis on that. So all this work was came about as a result of a study on sudden infant death after penta or hexavalent vaccinations in Germany. These are the results of those analyses. So the modified SCCS here in the table, that's the more complicated method. And the relative incidence associated with the 3 doses of vaccine or separately with all doses together. And then on the right, there's the results of the minimum separation method, that simple method. So there were 318 cases of sudden infant death. So the minimum separation was only applied to 90 of those 318 cases because only 90 cases kind of sat within that minimum separation window. Only 8 deaths actually occurred within 3 days of any dose. And we reached the same conclusions with either of those methods. The confidence intervals are always crossing 1 and therefore no significant association was actually found. So the self-controlled risk interval method. I'll just quickly run through what that is. It's basically a restricted self-control case series where we've got a fixed length observation period, which is defined in relation to exposure. So we'll usually just have a single vaccination risk window and 1 or possibly 2 control windows as you wish. The total observation time is usually short and the age effects are usually ignored. So where there's concern that outcomes influence the subsequent exposures, we can just take 1 control window which occurs after exposure. Oops. And we can put gaps in between the risk windows and the control windows. We can kind of set it up as we wish. Now, the beauty of the self-control risk interval method is that if all the cases have the same observation periods and there's no age effects, then the relative incidence simplifies to just this equation here. So this is really easy to apply to large databases. So all we need to know are the lengths of the windows and the counts of the adverse events within those risk and control windows. Another advantage might be that this could work for pooling without any need to share individual level data. We only need those summary counts. The relative incidence of a self-controlled risk interval study should be interpreted as a risk gradient between the risk and the control windows. I was just thinking about COVID-19 vaccines, because there's so little time between dose 1 and dose 2, if we're kind of running with the recommended schedules, it's not necessarily obvious where you would place your control window. And of course, being kind of restricted, it's less powerful than a full self-control case series study. Moving on to the last little bit. So we'll have a look at the COVID-19 vaccine safety studies that have been published so far. I could only actually find 3 in the published literature. And all of these studies are looking at dose 1. So there's a list of some of the events which have been covered in these 3 papers there. So I think all of them, as I said, are looking at just dose 1. They've used the standard self-control case series design. They've taken the first dose in vaccinated cases only, and they've censored at the 2nd dose or at death. So certainly in the Nature Medicine paper and the BMJ paper, the risk periods were set up a separate period for day 0. Which is probably a good idea generally. Day 0, we never know which came first, the event or the exposure. So it can be a useful thing to take that as its own separate risk period. But then they've got 7-day risk periods up to 28 days after the first dose. They've included a pre-vaccination period of -28 days up to the day before vaccination. And we've got 3 exposures. So the Oxford AstraZeneca vaccine or ChAdOx1, Pfizer vaccine or BNT162b2, and also positive PCR tests. So looking at the results of the Pantone et al. Nature Medicine paper, I've just put that in here as an example. So the top panel is the Oxford AstraZeneca vaccine in the UK, and they found a significant association 8 to 14 days and 15 to 21 days after Guillain-Barré syndrome. After vaccination for Guillain-Barré syndrome. They found a significant association 15 to 21 days after the AstraZeneca vaccine for Bell's palsy, and the same for myasthenic disorder. They didn't find any of those associations with the Pfizer vaccine, but they did see a slightly increased risk 15 to 21 days after the Pfizer vaccine for hemorrhagic stroke. And this bottom panel is the SARS-CoV, the PCR positive test. And we see that there's kind of quite strong associations with having the COVID itself and all of these events in this included in the paper. So let's kind of look at delving into the supplementary material in this paper, kind of to question some of the assumptions of the method. Just they've used a standard self-control case series design here. So these are plots which are centered on vaccination. They're horribly blurry, but that's how they were in the paper, and I've just kind of taken them as they are. So the red line is the timing of the vaccination. The black line is 28 days after vaccination. The green line is 28 days before vaccination. So that's kind of roughly where our pre-exposure period is set up between the green line and the red line. And then the main risk periods are set up between the red line and the black line. And I've also given the number of deaths for each of these events. So we see with most of the top panels, there's a kind of fairly balanced number of events before and after vaccination, before the risk period and after the risk period, but we do see that dip in the pre-exposure period, and with some of these we do see the kind of big spikes where the significant associations were found. A couple of these events which I was a little bit concerned about, particularly hemorrhagic stroke. Out of 3,503 events, there are 803 deaths, so that's 23% of the patients that actually died. And we can see in those analyses that the event rate looks like it's much lower in the baseline period before vaccination than it is afterwards. So that probably implies that, I mean, the deaths is a problem in itself, but also there's probably some long-term event-dependent exposure issue there. Certainly stroke, it can be a life-changing event, and patients are not likely to get vaccinated quickly after they've experienced a stroke. So these are the sensitivity analysis for the Oxford AstraZeneca vaccine on this page. So they'd found significant associations for Guillain-Barré syndrome and Bell's palsy, and that seems to not be affected by any of the sensitivity analysis. So I don't think we have any kind of concern with the findings there. If you recall, they found that significant association for stroke for the Pfizer vaccine, and these are the sensitivity analysis there. So if they exclude patients who died, that association actually disappeared. If they look at post-vaccination time only, the associations disappear, and in actual fact, there's a slightly reduced relative incidence in the 1 to 7 and 8 to 14 days after vaccination. That's probably showing that those patients were more healthy soon after they'd had their vaccination. There is one sensitivity analysis, this fourth one, where patients who didn't receive the second dose, so that's a kind of slightly concerning subset where it will include all the patients who died, and therefore the problem of event-dependent events is probably exacerbated there. I don't think, having looked at the sensitivity analysis as a whole, that they can really conclude that there is any association with stroke, and they do mention that in the paper. One last little slide before I conclude is on the case crossover method. So this is another self-controlled design, and I've seen it used for vaccines a few times recently. So it's more akin to a case control study. So the index is the event time, and it's analysed as for a matched case control study we determine the exposure status in the event window and in some control windows which are set up before the event. So the adverse event times are fixed and the exposure times are random in a case crossover design. The problem with a case crossover design is that it can be biased by any temporal or age trends in exposure. and the timing of vaccines doesn't tend to be random. So I think if where we do see case crossover method use, then we ought to be kind of a little bit cautious in interpreting those and thinking about whether they might have been biased by any temporal or age trends. So some final remarks. Self-controlled case series method, it can be useful when information on potential fixed confounders is missing. It's relatively fast and cheap. There's no need to collect information on controls, but it does have some very restrictive assumptions, in particular that assumption about events not influencing exposures. But there are some simple and complicated methods available to get around these for some certain circumstances. And for studies of COVID-19 vaccine safety, as they're extended to 2 doses, probably that dependent exposure extended method or time after vaccination only might be needed for some adverse events. And I'll just leave it with some further information. So there's a website, sccsstudies.info, where you can find various examples for ARS data and SAS. And there's just a couple of papers there, which are kind of good suggested introductions. But there's also a book which has got lots of examples with R. And my final slide is just references. But I shall stop there, and I think we can move on to questions.
Wow, Heather, that was amazing. And I first have to say thank you for the R. I was going to be my question, so I already took it out of my mouth. I'm really delighted to see this. And I know folks have been asking in the chat around the paper, so we'll make sure that reference gets distributed with your deck so folks have that. I see a question in the chat from one of our FDA colleagues. Some patients may have had recent COVID-19 infections. The Nature paper separately assessed the adverse events after COVID-19 infections to provide the context for interpretation. What would you recommend to adjust for different individual level AE due to recent COVID infections? Oh boy, that's a mouthful.
Sorry, sorry, could you, that wasn't mouthful. Could you say?
Let me try that one. And Cindy, actually, let me see, I can also unmute you if you would like to ask your question. I'll allow to talk. Cindy, perhaps, would you like to ask it live, since I'm a terrible transcriptor reader?
Sure. Thank you. Thank you. Probably because my question was not very clear. So thank you, Heather, first of all, for a wonderful presentation. So my question is regarding the Nature Medicine paper that you presented earlier, published by the UK group. So they also presented the risk for the adverse events after COVID-19 infections to basically contextualize the risk following COVID-19 vaccines. So in this case, basically what they're saying is different people may have different sort of like quote unquote underlying risk for adverse events due to recent COVID-19 infections. So what would you recommend to incorporate this factor into a self-control case series to actually adjust for it instead of doing a separate analysis just to contextualize the interpretation?
Yeah, so that was all done in one analysis in the Nature Medicine paper. So they had 3 different types of exposures all included in the one analysis. So the 2 different types of vaccination plus the actual PCR positives. So I think that's quite a good idea to do that. So I suppose infection could be thought of as a time varying confounder, which is going on in the background, and it's good to take that into account as they did there.
I see. Thank you.
We have one more question in the Q&A. It looks like Danny Pareto Alhambra is asking you about how the UK HSA is using a lot of test negative case control analyses for vaccine effectiveness. He was curious if you could give your 2 cents on the method and its pros and cons. And it looks like Danny is hiding under someone else's name. I'm going to allow, there are 3 Annikas, so I'm not sure which one is actually Danny, if he wants to comment.
Sorry, what's this on test negative case control for vaccine?
That it looks like, yes, there's a question on that. And I'm one of the 3 Annikas, maybe Danny, he can comment.
Yeah, that's me. That's the right Annika. Yeah, thank you very much.
Gosh, I don't know what to say about test negative case control. Yes, it is. I mean, the general idea is that only those oh, you've left me a little bit stumped.
Next question, then. That's fine.
Well, I heard Patrick has a burning question, so maybe I'll let him come in with his question.
Yeah, thank you, Heather. This was a great talk, and since we're seeing a rapid expansion of the self-controlled design, it's good for everybody to have a good foundation. So thank you for your talk, and just to prove that you got your royalties from me, I'd never leaves my desk. So there you go. One of the active debates that I've been hearing, particularly in the context of the COVID vaccine surveillance, is questions about censoring calendar time in the periods of time, for example, pre-exposure versus post-exposure, or like, in the before times when we didn't have a pandemic versus in the after times. And in general, I think that this largely falls into this idea that there may be time varying effects in a population that we're worried about. But there's some very practical issues associated with if we, for example, if we don't use pre-exposure time before the vaccine, that means we can only accrue our time at risk for the vaccine, and then we have to wait until there be a unexposed post-exposure time, and you're kind of waiting longer for that. I've heard a lot of epidemiologists making these kind of like arguments for why that's a pure approach to produce an estimate, but I haven't seen much firm data to argue against using pre-exposure time. And as you nicely presented, like the self-controlled design nicely handles pre-exposure time or handles unexposed time, whether it be before or after. So I wondered whether you could just comment on, and I'm sure you've seen a lot of this, people kind of imposing their own censoring on observation time. And if you have any recommendations, particularly in the context of the COVID work, whether or not you think it's a good idea to be restricting to only post-exposure time, or doing some sort of censoring otherwise.
It's all going to very much depend on the specific events under study. I know, I'm sure I saw a presentation, with one of these self-controlled risk interval where they're just kind of doing the risk identification, and they were using time before the first dose to look at the first dose, because there is kind of no time between dose 1 and dose 2 to have any post-exposure time. So I guess that was kind of driven by practicality. For some events, it's going to be fine. For other events, it's not. So I guess, it's just kind of the epidemiologist's job to think about where it is and it isn't sensible, worrying about things like mortality rates, worrying about, and then I suppose, we've got dose 1. If somebody has a particular event before dose 1, actually, it's probably not going to stop them from going to get the vaccine. So if we're looking specifically at dose 1, we're not going to get so much of an issue. But then if they have an event after dose 1, do they go on to get dose 2? then things might become a little bit more tricky. We probably, if we're looking at dose 2 only, perhaps it would be worth, I mean, at least as a sensitivity analysis, looking at only the post-vaccination time, just to kind of, you know, help you think about whether we've got this issue of event-dependent exposures going on. I don't, that's a bit of a rambling answer, I'm sorry.
No, that's very helpful. Maybe as a so any good answer usually is it depends, right?
Absolutely. It does very much depend on the events.
Yeah. So to that point, maybe it's just as a quick follow-up. One of the things we're really keen on thinking about is whether or not we can come up with empirical evaluations of some of these assumptions. Because what I'm personally concerned about is a group in the UK can make some set of assumptions about SCCS. A group at the FDA can make a different set of assumptions about SCS, and then you don't know whether differences in results are population, method, you know, data capture. Like, we have too many variables moving on at once. One approach we've been using in Odyssey is the use of negative controls as a way to try to evaluate method performance. So I'm wondering, in this idea of like using pre-exposure time or not using pre-exposure time, would you be reassured if you saw a large panel of negative controls basically showed the same answer? Would that be sufficient to say, let's use the larger powered use of the pre-exposure window, or would that also kind of depend on the outcome?
Yeah, I think use of negative controls is a great idea. But again, it's just going to depend on the outcome. I know you want to set up something objective that works for everything. Perhaps in practice, it's not quite so easy.
Well, lucky for you, Heather, we have just hit the end of time, so you don't even have to answer it. You can leave it as food for thought that we should think about in 2022. I just want to say on behalf of our whole team, thank you so much for closing out our 2021 series. I really enjoyed today's talk, and I look forward to learning more about the R code that you have in that resource. We can't wait to share this with our colleagues to keep the conversation going. Maybe Patrick will send you a few more zingers and follow up. And thank you all for coming today. There's a link in the chat. We'll be reconvening in January going forward, and we look forward to finding that silver bullet. Maybe next year, our to-do list, we'll find that one. Thank you so much, Heather. We really appreciate it.
Thank you.
Thank you, Heather. This is wonderful. Appreciate it.